Hey guys, can you hear me?
Yeah.
Good, thanks. Okay, so today is the last class we're gonna have before the review, and then we're gonna have the test. I haven't seen any sample problems, any sample test yet on 231, but there is a sample in 230. So if nothing is added to 231 by Thursday, we're basically going to go over this sample test. Number one is a question that might be asked. The final is cumulative, but mostly we'll focus on critical points and stuff like that, Lagrange multipliers. But number one definitely can be asked. Number two can be asked. Number three can't be, it's an integral. Also, number four is an integral, so we don't need to focus on that. Number five is a question that we can see. Also, number six. Number seven, again, is an integral. Number eight is an integral. Number nine is a possible question. And number 10 is also a possible question. So today I'm basically going to look over Lagrange multipliers again, even though I sent 2 videos for you to watch. It would still be useful, and then that would be the end of this class. And the last topic that we will cover will be Lagrange multipliers. So in essence, what we're trying to do with Lagrange multipliers is find critical points of a function, but subject to some constraints. So we can imagine that we have some function f. So this is our function f of xy, and we want to find the critical points, the maximum and the minimum of this function, let's say subject to the constraint that we're on a circle of radius 2. So this would be the function g of x this would be the function g of x, y, maybe it would be x squared plus y squared is equal to 4, and it would constrain the possibilities of the points that we're looking at. So we're not looking at this point over here or some point over here. Instead, we're only looking at points lying on this constraint over here, and we're trying to find the maximum or the minimum of the function f subject to that constraint. So the way we do it with Lagrange multipliers, and we can do it using techniques that we saw before, like cut this domain into 2 pieces and turn this into a single valued problem. But the easier way to do it is with Lagrange multipliers. So we take our function f, we take the x derivative of it, and we set it equal to lambda times g of the y derivative, sorry, of the x derivative. And then we do the same thing with the y derivative. So f of y is equal to lambda g with respect to y. And this is the system of equations that we look at. And once we have it, we need to find our lambdas, our x's, and our y's. And we can use this function also. So it's this function plus this, use it to find lambda, x, and y. So let's do an example. So they tell us to find the maximum and the minimum of the function f, which is equal to 2x plus 5y. So f xy is equal to 2x plus 5y, and g of xy is equal to x over 4 squared plus y over 3 squared is equal to 1. X over 4 squared plus y over 3. Good. So these are our two functions, and the constraint is the low one. So they find the extreme values of this function on this ellipse. So that's the constraint. So the way to do this is by taking the derivative of f with respect to x, which is 2, and setting it to lambda times the derivative of g with respect to x, which is going to be 2x over 16. So that's the first one. The second one is taking the derivative with respect to y, which is phi of f, and that will be equal to lambda times 2y over 9. So our two equations are 2 is equal to lambda 2x over 16, and 5 is equal to lambda 2y over 9. Now we know that x and y are not going to be equal to 0, because otherwise the left-hand side wouldn't be 2 and 5. So we can divide by x and we can divide by y to solve for lambda. So the first one gives us lambda is equal to 32 over 2x. And the second one gives us lambda is equal to 45 over 2y. Now we can set the lambdas equal to each other to figure out what y is in terms of x, or what x is in terms of y, whatever. So we are going to get 32 over 2x is equal to 45 over 2y. And this will tell us that 2 times 32 over 2 divided by 45, and this so then we could have a y here. This thing is equal to x. Right, is that correct? 1 second. So 45, yeah, it comes down, 2 goes up, and then the y goes there, x goes there. Looks good. Okay, so the 2's can cancel, and we get that. So now we can plug this back into the original equation g. So this equation right here, putting it for x. So that's x over 4. So we're going to have 32y over 45 over 4 squared plus y over 3 squared is equal to 1. Okay, so now we can take out the y squared. So we have y squared times 32 times 4 over 45 plus 1 over 3 is equal to 1. Or in other words, we get y squared is going to be equal to 1 over 32 times 4 over, oh, sorry, these are also squared. Yeah, so this is squared. No. This over here is squared, and this is going to be 1 over 9. So this is 1 over 32 times 4 over 45 squared plus 1 over 9. So that's what our y is squared. And so then y is going to be equal to the square root of plus or minus 1 over 32 times 4 over 45 plus squared plus 1 over 9. So these are our critical points, the plus and the minus. And that would be for our y. And then we can plug it into this equation over here. We can plug our y into this equation to get our x. Now, because these are very complicated, I'm not really going to do it, and I'm not going to figure out what the critical points are. But on the test, it should not be this complicated. And you should then be able to plug it into the function f. So plug all the points that we get. Over here, we would get 2 points. So we'd get p1 P1 is equal to X comma Y. P2 is equal to X comma Y. And we would plug that into our F of P1, see what that is. F of P2, see what that is. And that would solve this Lagrange problem. Any questions about that? Okay, so they do something similar. They get the P, they get another point Q. They plug it into the F, they get 17, and Q is negative 17, so the minimum is negative 17. Okay, now we don't have to do Lagrange multipliers with more than 2 constraints, so I'm going to ignore that. And I think this is basically the end of the section. I mean, this is Lagrange multipliers with 3 variables, but it's very similar to what we just did. You again have F, G, and you just take, so here's your G. And we want to find the point closest to the origin, and that would be a function which is represented by the distance. So that's squared of x squared plus y squared plus z squared. So we want to minimize our f, which would be x squared plus y squared plus z squared. And we then have our g. We take the gradient on both sides, which would be the same as, so now our function is x, y, z. Sorry. X, y, z is equal to x squared plus y squared plus z squared. And obviously, if you minimize this, you will minimize the distance to the origin, because minimizing this would be the same as minimizing this with the square root. And so then we take the gradient of this, or the partial of f with respect to x, and set that equal to lambda partial of g with respect to x, partial of f with respect to y, set that lambda g with respect to y, partial f with respect to z equal g, lambda g with respect to z. So we get that. And so then on one side, we're going to get 2x, 2y, 2z. And on the other side, we're going to get lambda 1/2, 1/4, 1/4 from this constraint over here. And I don't believe that this is relevant to that problem, but okay, here it is again. Okay, and then one second. So then once you have this over here, you can solve for your x, for your y, and for your z. So you can, in terms of lambda, so you can say that, okay, x is going to be equal to lambda over 1/4, y is going to be equal to lambda over 1/8, and z is equal to lambda 1/8, 1/8. So this would be your x, your y, and your z. Now you can plug that into your constraint to solve for lambda. So we can plug it into our constraint to solve for lambda right over there. -1 is equal to 0. That will tell you what lambda is. And then you can plug the lambda into all of these to figure out what x, y, and z are. So once you figure out what lambda is, so plugging it into here, you're going to get lambda 1/4 over 2. So it would be 2/4 plus lambda. And then you're going to have 1/8 over 4. So that's 4/8 plus lambda, again, 4/8. And all this should be equal to 1. So then you're going to have lambda 2/4, so 1/2 plus a 1/2 plus 1/2 is equal to 1. And this over here is 2/3. So lambda is going to be equal to, 3/2. So that would be 2/3. And then you would plug this into here, your lambdas to figure out what that is. So now my x is going to be 2/3 times 1/4, and so on. And then you plug this into your distance, and that would tell you how far away you're going to be from the origin, at least. Or it would give you the x and the y and the z that satisfy this. So you would already have the point closest to the origin. You would have your x. This is your x. And so on. Although the coordinate, one second. I'm not sure that this is related to this problem. I don't know. Because this is a critical point with the greatest x coordinate, maximum value of this. So, okay, and here it's the closest. So I don't even know if these are connected. Let's see, 871. And this is 869. So it's not. Okay, anyway, so that would be your x, your y, and your z, and you'd be done. Any questions about that? Okay, then if there aren't any questions, so let me just repeat briefly what I said in the beginning of class. We are going to finish with Lagrange multipliers. So this is the last section we are going to do. If next time a sample exam is posted on 231, we're going to do it. Otherwise, we're going to do this exam, focusing on problems 1, problems 2, 5, 6, 9, and 10. Okay, for example, in problem 6, they want us to find the extreme values of this function on the elliptical region, this. And in the interior, you can use what we learned last time, but on the boundary, you can either break the boundary up into 2 and do what we did before, turn this into a single valued problem, or turn the f of x, y into a single valued problem, or we can use Lagrange multipliers in this example. Okay, so that's basically what we'll be doing next time. Are there any questions?
Will we be having a quiz before the exam?
No. Any other questions? Okay, so if you do have any questions, you can email me. If you want to go over problems, I'm happy to go over problems. Okay, have a nice day, and I'll see you on Thursday. Bye.